So, welcome to the first unit of this course. In this unit, we will be studying about waveforms and signal spaces, and today is the first lecture of this unit. Okay. So, let us start. This is the outline of the lecture. First, we will see why it is important to be able to treat waveforms as vectors. We will also answer the question, what are waveforms? Then we will study what are known as L1 and L2 spaces, indistinguishable functions, and finally, we will talk about bases and linearly independent vectors. Okay. So, let us see the objective of this unit. In this unit, we would be developing framework which would allow us to treat signals as vectors, and once you can convert signals into vectors, the signal becomes a point in a vector space, right. So, you will have a vector space and signal will be just a point in a vector space. Normally, you would have seen in the courses like in signals and system that signal is either a function of time or signal is either a function of frequency, right. But here what we would be doing is we would be able to convert signal into a point in a vector space, and this will be very useful and helpful. And with this we would be able to define how close the two signals are, what are the angle between the two signals, and so on and so forth. Okay. So, this is a really important unit for this course on principles of digital communications. Okay. So, let us see it more clearly. To understand this, let us start with the simple receiver. We have already talked about the additive wide Gaussian receiver. So, it's a receiver like this. Here we have this input. So, this is the input, and to this input we have some noise addition. So, noise is additive to the input, and this is the output of the receiver, x plus y. Now, let us assume for simplicity that x takes in a value from this set. So, either it can transmit 0, 5 or 10. So, this is a finite set. So, we know that we are in the regime of digital communication, and let us assume that y takes in a value between -1 and +1. So, noise is limited or the noise amplitudes rather are limited between -1 and +1, and what arrives at the receiver is a combination of a transmitted signal and a noise. Okay. Now, what receiver does is it first maps these possible transmitted values on a real line. Okay. So, it maps this transmitted value 0, 5 and 10, and let us assume that the received value bumps up this real line on a certain point, let us say a point A. Now, what does a receiver do is it calculates the distance of the received value from the possible transmitted signals. So, it calculates, let us say this distance, I call this as d1, it calculates this distance, I call this as d2, it will calculate this distance and I call this as d3. So, it calculates distance from all possible transmitted values, and then what it does is it finds out the transmitted symbol or signal with minimum distance. Okay. So, in this case, for example, d2 is minimum out of this d1, d2 and d3, and thus it selects 5 as the possible transmitted signal. So, receiver decides that 5 must have been transmitted, and so things looks very simple. As now there are no real complications involved in this. Of course, we have simplified this problem a lot, right. We have converted a complicated problem into toy of the toy problem, but if we can do or if we can convert the signals into numbers, we have not said whether the signals are numbers, but if we can convert signals into numbers, this problem of reception and deciding what has been transmitted looks rather a simple problem. Okay. So, now this is what we are saying. So, in reality a transmitter would transmit signals. So, it would transmit S1t, S2t and S3t. Now, if we are able to convert these signals into vectors, for example, we have been able with some framework, we have not talked how, but let us say there is some framework which allows us to convert the signal into a vector, where this signal can be understood by some real numbers, then we can do what we did just previously. So, we can talk about the distance between the two signals, we can talk about the angle between the two signals, and so on and so forth. So, whatever you have studied about vectors applies here now, right. So, with this framework. So, this framework allows us to talk about the distances between the two signals, angle between the two signals, and we will be able to convert signals into numbers, and things will become really simple. And so, this is what we are trying to learn in this unit, how to do this. Okay, so, let us start, and first thing that we have to learn is what are waveforms. Okay. So, we have already seen a hint what are waveforms in the first lecture, and we would be talking more about this today. So, waveform, as we have already stated, is a function, and it is a function with independent variable as time. It is a continuous time function, right. It is something that can travel over channel, it is something that could be produced by electrical circuits. So, it is a continuous time function with independent variable as time. What is a function? You must have studied about function. Function provides mapping between domain and range. So, if I talk about a function, a simple function, just to understand and get things started, if I take a function as t plus 1, then this function provides a mapping between domain and range, and t is the independent variable. Okay. So, t is an independent variable, and the functions of interest in this course, the independent variable is always time and maybe sometimes frequency, but mostly it is time, and this is giving us the range of the function. Okay. And it is providing a mapping between domain and range. Okay. So, for example, if domain takes these values, then the range can be simply obtained by just adding 1 to this. So, this is a very simple example of function. Function provides a mapping between domain and range. Okay. And waveform is a function with independent variable as time, it is a continuous time function. Now, the functions can be of two kinds, it can be a real valued function or a complex valued function. Now, because we have said that the functions in which we are interested in, the independent variable is time, right. So, it is a function like f of t, independent variable is time. Now, time is always a real quantity, right. Time is never a complex quantity, it is always a real quantity. So, these functions would be providing mapping between real space, because time is always real, to a real space. That means, the value of this function can be a real value, or it can provide mapping between real space to complex space. That means, f of t can take a complex value, right. So, we can have two kinds of functions, the functions which provide mapping between real space to real space or real space to complex space. These functions are known as real valued functions. The functions which provide mapping between real space to complex space are known as complex valued functions. Mathematically, if we denote this as this real valued functions, the functions which provide mapping between real space to real space, and complex valued functions, functions which provide mapping between real space to complex space. This is real because we are always taking independent variable as time. Okay. So, we would be interested in these kind of functions, real valued or complex valued functions. There is abuse of notation that is normally being done in engineering textbooks, and we will continue to do that. And this is that when you write f of t, normally this will mean the value of function at time instance t. Okay. But when we are writing f of t, it simply means that this is a function where the independent variable as time, and it means that time can take value in the real space. So, time can take any value between minus infinity to plus infinity. Now, to talk about the specific value of this function at, let us say, at a specific time instance, let us say that we are interested in a specific time instance t naught. So, this is how we would be differentiating between a specific instance of time and the time as an independent variable. So, when we are saying t, it simply means that time is independent variable. When we are saying t naught, it means that it is a specific value of time. So, when I am talking about f of t naught, it means that this is the value of a function at a particular time instance t naught. When I am just writing f of t, it simply means that this is a function with independent variable as time. So, this distinction has to be made. This is not precisely how things should have been done, but this is what has been done in most books, and we will continue to use this notation. Okay. Now, normally the functions can take more than one independent variable, right. So, we have been looking for functions with one independent variable, but the functions in general can have more than one independent variable. For example, let us look at this picture of dog. This image is also a function, right, and this function could be constructed by knowing the intensity of this image along x and y coordinates. So, this is a two dimension function. It has two independent variables x and y, but luckily in this course we will only be talking about one dimensional functions or one dimensional signals. So, things are pretty easy in this course. Okay. So, this is the last point, that we only deal with one dimensional signals or functions in this course. I am using this word function and signal interchangeably because they are so. Okay. So, what we have done, we have already understood the objective of this unit, which is trying to treat signals as vectors, and we have already defined what are waveforms. Waveforms are functions with independent variable as time. We only talk about one dimensional signals or functions in this unit. Now, let us see what are L1 and L2 spaces and L1 and L2 functions or signals, and what are these indistinguishable functions. Okay. So, let us first define what is an integral of a real valued signal. So, real valued signal provides a mapping between real space and to real space, and this is how the integration of a function is defined. Everyone must have learned the integration in high school or secondary schools and so on and so forth. So, how do we do integration of a function? Now, the one way to think about doing the integration of a function, and the way we have been taught mostly, is we take a function like this is a function which spans from 0 to t seconds, and when you calculate the integration, basically you are interested in finding the area under the curve, and the simple way to do this is to divide this function into chunks. Let us say we have divided it into n chunks, right. So, the width of each chunk would be t by n. Okay. Now, to calculate the area under this curve, what you can do is you can break this function into chunks with width of t by n, and you find out the value of this function in each chunk. For example, in this chunk I can approximate the value of the function as u1, of course, if this width has to be pretty small, right. So, I can approximate the value of this function in this chunk as u1, and then the area in this chunk would be u1 times t by n, because the width is t by n. And similarly, I can find the area under this function by summing up the areas corresponding to each chunk, and this is what we are doing. So, we have to find the area of one chunk, and then we have to sum up the areas of all chunks to evaluate the integration of this function, right. This approach of finding integration is known as Riemann integration, right. You can also interpret integration in other ways. For example, you can think about integration using Lebesgue approach. And what is that approach? Instead of discretizing the time axis, so this here we discretized the function along time axis. What you can also do is you can discretize the function along y axis, right. Instead of x axis, you can discretize it along y axis, right. So, now what you can do is, let us just focus on one part. Let us say this function takes in the value 3 delta, and let us now, in order to find the area of this part, how can we find the area of this part? Would be 3 delta times the time interval for which this function takes in this value of 3 delta. For example, in this case, these time instances t4 minus t3. So, I have to take this. So, the width is t4 minus t3, and then there is a second part, the width would correspond to t2 minus t1. So, this is the total time for which this function takes in a value of 3 delta. So, the area corresponding to this could be obtained by multiplying 3 delta with this thing. So, this is also known as the measure of the function. So, the idea is similar. Instead of discretizing along time axis, you have discretized it along the amplitude axis, right, and then you are finding the area for each chunk and then you are summing this up. So, this is known as the Lebesgue approach. Now, whether you take the Riemann approach or Lebesgue approach, for most functions you would have the same output, right, but for certain functions the Lebesgue integration would give a different result than Riemann integration. So, all integrals in this course are understood as Lebesgue integrals, and this is because when we are stating theorems, we want to state them precisely, and some theorems are only applicable if you consider the integration as Lebesgue integration. So, we will like to think about the integrals as Lebesgue integrals, okay, just for preciseness. Now, we can also define whether a function as integrable function if it follows the two conditions. The first condition is function must be a Lebesgue measurable function, and the second condition is that the integration of mod of that function should be finite. If these two conditions are satisfied, then we say that the function is integrable function, right. So, two conditions: first, Lebesgue measurable, it should be a Lebesgue measurable function, and integration of mod of that function should be a finite thing, right. If the function is integrable function, we say that the function belong to L1 space. So, the set of all integrable functions is denoted by L1 space, okay. Now, if you want to define this thing for a complex valued signals, so far we have been just talking about real valued signals. So, what happens if we want to talk about these things for complex valued signals? The same thing happens, just because it is complex, you can break this function into two parts, real part and imaginary part, and now you apply the condition for integrability for each part individually, right. So, you have to say that these things have to be Lebesgue measurable functions, and the integration of mod of real part of f t should be finite, and integration of mod of imaginary part of f t should be finite, or in one go integration of mod of f t should be finite. Okay. We have not yet talked about what are Lebesgue measurable function. We have just said that the function has to be a Lebesgue measurable function. Now, trying to understand what are Lebesgue measurable functions is really complicated, and we have to restore to measure theory to understand what are Lebesgue measurable functions. But luckily, most of the signals and functions that we will be dealing in this course will be Lebesgue measurable functions. In fact, it is very difficult to find an example of a function which is not Lebesgue measurable function. All functions are virtually Lebesgue measurable functions. So, we will take it for granted that the functions that we will be dealing with will be Lebesgue measurable functions. So, that is not so strict condition. The more important condition would be trying to find out whether the integration of mod of a function is finite or is not finite. Okay. So, now let us study about L2 waveforms. So, we have already talked about L1 waveforms, and there was that function has to be Lebesgue measurable function, and integration of mod of that function should be finite. So, what is that thing in L2 waveforms? So, for L2 waveforms, the function has to be Lebesgue measurable function, and integration of mod square of that function should be finite. So, when talking about L1, we were interested that this quantity should be finite, integration of mod of function should be finite. Here we have a square, okay. So, integration of mod square of function should be finite. So, if you have done a course in signals and system, you know that this quantity is telling me the energy of the function, right. So, this quantity corresponds to the energy of the function. So, one way in which we can define L2 waveforms is that class of all finite energy signals, right, because if this quantity is finite, that means we are saying that energy of the signal should be finite. So, the class of all finite energy signals belong to L2 space, right. Now, can we have signals which have infinite energy? Answer is no, right. If you could have signals with infinite energy, then the energy crisis of the world could have been solved. So, we do not have any signal with infinite energy. So, practically all signals that we deal with have finite energy only. But mathematically we would be interested in certain functions which have infinite energy, and thus we have to be really careful when we are dealing with those signals. Okay. Now, one important advantage of these L2 waveforms is that L2 waveforms are vectors. You can treat these L2 waveforms as vectors, you can use the ideas of signal spaces, you can do simple things, right. Secondly, L2 waveforms always have Fourier transform and Fourier series. So, you must have studied these tools in signals and system course, that you can go from time domain to frequency domain, you can go back and forth using these tools, and all this theory is applicable if the underlying signal is an L2 signal or is an L2 waveform, right. So, L2 waveforms comes with lot of advantages, means you can use Fourier series, Fourier transform, you can use the ideas of signal spaces, and all practical signals anyway are L2 waveforms. So, most of this makes sense. Okay. Let me test you with one question. We have 4 signals here. So, we have cos omega t, we have ut, which means unit step, we have delta t, which means unit impulse, I have sin t, which means sin t by t, and you have to find out whether these signals are L1 signals or L2 signals. Now, let us look them one by one. So, let us start with cos omega t. So, cos omega t you can see is neither L1 nor L2, unit step is neither L1 nor L2, unit impulse is L1, but it is not L2, sin t is not L1, but it is L2. So, the first thing that you should appreciate is the function can be an L1 function, but it need not be L2. For example, delta t is an L1 function, but it is not an L2 function. Okay. The function can be L2 function, but it need not be L1, right. For example, sin t is L2, but it is not L1. So, there are functions which are L1 but not L2, there are functions which are L2 but not L1, there are functions which are both L1 and L2, there are functions which are neither L1 nor L2. Okay. So, from one you cannot make easy conclusions about the other. So, let us see how can we think about whether the functions are L1 or L2. To think about this, let us start with cos omega t. So, in this we would be making very intuitive proof, right, we would not be going through rigorous mathematical proof. So, how can we think about whether this cos omega t is L1? Let us first start with L1. So, when we are talking about L1, we are interested in integration of mod of that function. So, for cos omega t, if I think about one period, this integration of mod of that function would be a finite quantity, right. Whatever is that, it is not interesting, and this cos omega t runs from minus infinity to plus infinity. That means you are multiplying a finite quantity with infinity, and so this would be giving us infinity. So, this is not an L1 function. Similarly, for L2 you need to check whether this is finite or infinite, and again the same logic holds. When you do this in one period, you will end up with a finite quantity. Again, because cos omega t runs from minus infinity to plus infinity, you have to multiply a finite quantity with infinity and you will get infinity. So, cos omega t is neither L1 nor L2. What about unit step? Unit step also you can think unit step goes from 0 to infinity, takes in a value 1, and because it exists for infinite duration and it exists for infinite duration with a value 1, this is also not going to be L1 neither L2. What about delta t? So, if we are talking about delta t, this is interesting. Let us check whether it is L1. Let us first define delta t. Let me assume that delta t takes in a value 1 by epsilon between epsilon by 2 and minus epsilon by 2, where epsilon is very small number. So, if I am interested in integration of mod of delta t dt, I get 1 by epsilon dt, it runs from minus epsilon by 2 to plus epsilon by 2 and you get 1. If I do this for delta t square dt, I get 1 by epsilon square into epsilon, and this turns out to be 1 by epsilon, because epsilon is very small quantity, this will approach infinity. So, clearly this is L1, but this is not L2. Let us now check for sinc t. Now, proof for sinc t would be most complicated out of 3 of them, but we can use one idea that sinc t, because it is represented as sin t by t, and sin t is an oscillatory function, it goes from minus 1 to plus 1. So, this sinc t for large t's can be approximated as 1 by t. So, sinc t decays as 1 by t, whereas sinc square t would decay as 1 by t square. Now, because this sinc square t decays faster, you can prove that this is an L2 function, and because sinc t decays slower with 1 by t, this is not going to be finite. So, this would be infinite, and this will not be an L1 function. This will be an L2 function because this quantity is going to be finite. So, you can simply check whether 1 by t dt, you can check this will be close to infinite if it runs from minus infinity to plus infinity, whereas 1 by t square dt is going to be finite. So, this is not a rigorous proof, but this gives you some idea to interpret about these sinc t's, and this is an important idea which we will use later on as well. So, remember the sinc t decays with 1 by t, it is not a fast enough decay, right. So, if you integrate that function from minus infinity to plus infinity, you would have infinite values, whereas when you are considering 1 by t square, this decays faster. So, even if it spills from minus infinity to plus infinity, because it decays faster, the area of 1 by t square would be a finite quantity, and this is intuitive way to understand why sinc t is not L1, but it is L2. A rigorous proof of this could be obtained from Fourier series and transforms, and I leave this to you to think about how can you prove the same things rigorously mathematically using the ideas of Fourier series and transforms. Okay, so let us move on and let us try to find out another important idea, and that is thinking about sets of functions with Lebesgue measure of 0. Now, let us start this by asking a question. So, if you are given that integration of mod of a function is 0, what are the possible values of this f t? So, what can be that function? Now, a simple function that would satisfy this equation would be an all 0 function. So, a function which is all 0 would definitely satisfy this, right. So, if you take the function, if you take that mod of a function, this mod of this function will also be an all 0 function, and if you pass this through an integrator, you are going to get a flat 0, right. But are there other functions which satisfy this equation still them being not all 0 functions? Yes, there are functions, for example functions like this, right. So, what is this function? This is a nasty function which complicates things in digital communication, and this function takes in some values only at discrete instance of time. So, let us say that it takes in some values for time instances t1, t2, t3 and t4. Now, what happens if you take the mod of a function? The mod of a function would give you the same thing if I assume this ft is all positive and real. So, taking mod does not make any changes, and now if I pass this function through an integrator, what happens? Now, if you look, let us just focus on one point. So, if I pass this through an integrator, because there is no width, integrator calculates the area, right. So, because there is no width, the function exists only at a single point, there is no width. So, once you pass this thing through an integrator, you get 0. Similarly, the contribution to the output of these points will also be 0. So, passing this function through an integrator would give you an all 0 signal. So, this is also a valid solution to this equation. So, there are two valid solutions kind of. So, one is an all 0 signal, that is good, and the second are the set of functions which takes values only at discrete instances of time, right. So, because at the points there is no width, when they are passed through an integrator, you are going to get a 0. Okay. Now, with this idea we can define what are known as indistinguishable functions. So, the functions, two functions are referred to as indistinguishable functions if you subtract the two functions and you get a function which is like an all 0 function, right. It need not be an all 0 function, it may be like an all 0 function. For this, for example, this function is also like an all 0 function, because once it passes through an integrator you get an all 0 thing, right. So, when you are having the systems are normally built using integrators, multipliers and adders. So, once you pass this function through an integrator, anyway you are going to get 0. So, whether you feed this to a system or to this to a system, you get the same answer 0, right. So, this is also like an all 0 function. Okay. So, for indistinguishable functions we have to take two functions, we have to subtract them and we have to see whether we are getting a function which is like an all 0 function, because if this is the case, then you can say that two functions are indistinguishable functions. For example, I have taken these two functions, I have taken u and I have taken a function v, and let us subtract it. What you are going to get is a function like this on the subtraction of u with v. Now, this is like an all 0 signal, because passing this through an integrator is going to give you a 0, right. So, these two functions are indistinguishable functions, you cannot distinguish between the two of them, right. More precisely, we can define indistinguishable functions as the functions which are different only at countable number of points. We have already seen in the first lecture that the countable set is the set which has 1-to-1 correspondence with a set of integers. So, we will use this idea to further define what is known as equivalence class and so on and so forth. Okay. So, we have covered the three parts of this lecture, seen the objective, waveforms, we have seen what are L1 and L2 spaces, we have seen what are these indistinguishable functions, and now it is our time to look at vectors, because this is what we are aiming for. We are trying to establish an equivalence between L2 signals and vectors. Okay. So, let us start by looking into these spaces and linearly independent vectors. So, the first thing that we have to see is what are these vector spaces. So, vector space is a space which consists of some elements, these elements are known as vectors, it has some set of scalars and it has some set of rules, right. So, this is a very basic definition of a vector space, something which consists of vectors, it has elements which are vectors, it has scalars and it has some set of rules. So, that is what is a vector space. Now, these scalars can be real numbers, these scalars can be real, and then we are talking about real vector space. These scalars can be complex, and then we are talking about complex vector space. So, we can have vector spaces of the two kinds, real vector space, which means that the scalars involved are real. We can have complex vector spaces, that means the scalars that are involved are complex, and of course, in neither of these vector spaces infinity is included. So, throughout this lecture we will be taking the examples of vector spaces which are real vector spaces, but you can easily extrapolate whatever we say for real vector spaces for two complex vector spaces. Okay. So, let us get started. Let us get started with very simple thing, the one thing that you must have seen before. When you are talking about the vectors, for example, we have now a 2D vector, 2-dimensional vector. This 2D vector can be understood as a vector which has two real numbers. Okay. So, when you are talking 2D vector, it is equivalent to having two real numbers. So, in this case you have two real numbers x and y. Remember, we are just giving examples from real vector spaces. Now, this x, as you know, would correspond to the value or the projection of this vector along, let us say, I coordinate, and y corresponds to the value or the projection of this vector on this j coordinate. Okay. So, this is what you must have done. So, 2D vector, remember, as we have said, is denoted by two real numbers. Okay. Now, the set of all 2D vectors would consist of 2D vector space. So, if you take all such 2D vectors, if you make a set of all 2D vectors, then what you end up with is a 2D vector space. Example of a 2D vector space is like the plane of paper, or it is computer screen, and so on and so forth. Okay. So, this is what you know from before. Now, if you have a 2D vector, what you can do is you can have another 2D vector. So, if we have a 2D vector here, I can take another 2D vector and I can add these two vectors. So, vector addition is defined, it should be possible. Once you add the two 2D vectors, what you end up with is another 2D vector. Okay. So, addition of a 2D vector with a 2D vector should give you another 2D vector. So, vector addition is possible. What I can also do is I can take a vector and multiply this with a scalar to change the length of my vector. So, this is known as a scaling operation. Take a vector, multiply this with a scalar. So, here I show for a scaling operation. So, vector scaling is also allowed. So, vector scaling is allowed and vector addition is also allowed. Okay. I can talk about the 3D vectors as well. The 3D vectors are represented using 3 real numbers. So, instead of 2, now we have 3 real numbers because the dimension is 3D. Okay. Similarly, as in the case of 2D vectors, the vector addition is allowed. That means you can take in another vector, you can add up these two vectors to get a 3D vector. So, I have taken a vector v, I have taken a vector u, and I have added these two vectors to get another vector v plus u, which should also be a 3D vector. I can take this vector and I can scale this up by multiplying this with a scalar. So, scaling operation is also defined. Okay. So, after scaling operation also the dimension of the vector remains same. So, I can extend this concept to ND vectors. So, n dimensional vector spaces. So, in 2D 2 real numbers, 3D 3 real numbers, ND it should be represented by n real numbers, right, and we also call this as n tuples. So, you have an array of n real numbers, that is what we simply also call as n tuples. Now, mathematically, if you have to prove that something is a vector space, you have to prove that certain axioms or properties are satisfied, and now we will be going through those properties to see what they are. As we have said, if you have two vectors, you can add the two vectors to get another vector. So, vector addition is defined. So, addition is defined, the order in which you add these two vectors does not matter, right. So, vector addition is commutative. Okay. There always exists a 0 vector, which means that if you add the vector with a 0 vector, you get the same vector. Okay. So, 0 vector exists, addition of a vector with a 0 vector should give you the same vector. Then an inverse of a vector also exists. That means you can have an inverse vector which when added to the original vector. So, this is an inverse of this vector, what you get is a 0 vector. So, inverse of a vector must also exist. Then vector addition is also associative. You add v plus u plus w with this bracket involved, and this would be same as this thing. So, vector addition is associative. So, all these properties corresponding to vector addition must be satisfied. Now, in the case of the vector space, we have already seen that scalar multiplication must also be satisfied, and it should be satisfied by following these properties. So, distributive properties in the scalar multiplication must be satisfied and associative properties must also be satisfied. I will not be reading out these properties because I feel that these are very simple properties. Moreover, we should also have a unit vector. What is a unit vector? Unit vector is a vector by which if you multiply any vector, you get the same vector. So, there must also exist a unit vector. So, in short, we can say vector space is a space where vector addition is defined and scalar multiplication is also defined, and these are defined in such a way that the properties that we have listed out are satisfied. Let us take an example with this n tuples, and let us say that I have a vector v which is set of n real numbers, I have a vector u which is set of n real numbers again, and I can define the vector addition by taking an element from v and by taking a corresponding element from u and adding these two things together. Okay. So, we make an element wise addition, okay. As demonstrated here, you have added v 1 plus u 1, that forms the first element of vector v plus u. You can define the scalar multiplication as simply multiplying each element by this scalar. Okay. So, this scalar multiplication is also easy. Now, I leave the proof to you to prove that if I define the vector addition in this way and scalar multiplication in this way, then this satisfies all the properties of a vector space. Okay. So, this you can prove yourself. Let us move on to an interesting question. Is L2 space a vector space? Yeah, now we have something at our disposal which we can use to prove that L2 space is a vector space. And what are those things? We know which property should be satisfied, and let us define first the addition of two L2 signals and the scalar multiplication of two L2 signals, and let us then check whether these satisfies all axioms corresponding to vector space. Let us get started. So, addition of two vectors, addition of two L2 signals is easy, is trivial, you must have done it several times before. You just take the two signals and add them. A scalar multiplication of a signal is also simple, you just multiply the signal with an scalar. Now, if you have these two definitions of how you would want to add two L2 signals and how you want the scalar multiplication to work on an L2 signal, I leave it to you to prove that this indeed satisfies all properties of vector space, and this will prove that L2 space is actually a vector space. One simple point that you might think about, slightly difficult to think about, is if you have u and v, if u and v are L2 signals, is it guaranteed that u plus b is also a L2 signal? That means, is u plus v is also a finite energy signal, is it guaranteed? Let us check. Let us check by simple properties from complex numbers that you must have studied, which says that this quantity should be less than or equals to this quantity plus this quantity. This quantity is finite, this quantity is also finite because these are L2 signals, then this quantity should also be finite. Okay. So, addition of two finite quantities should give me a finite quantity. This is intuitive. If you are adding up a bunch of finite energy signals, then the energy of the signal should remain finite, otherwise we could have created energy easily. Okay. Similarly, we can prove for scalar multiplication as well. If you have a finite energy signal, you multiply this with a scalar which is a finite, then the resultant signal should also be of finite energy. Okay. So, L2 space is a vector space. You add two L2 signals, you get another L2 signal. Now, let us talk about these vector spaces little more, and let us again fall back to our example of this 2D vector. So, I have a 2D vector again. I have represented this like this xi plus yj, and you must have seen this representation before. What we are saying is I and j are perpendicular vectors and so on and so forth, as usual, as by convention. Now, to generalize this, I can write this as in this term, where instead of x I have a1 and instead of y I have a2, and by changing in these values of a1 and a2 I would be able to span the complete 2D space, right. So, the complete space could be spanned if you change these values of a1 and a2. I can also generalize this further. I can write this vector as a linear combination of two vectors. Rather than I and j, I can have a vector v1 and v2. I am doing the same thing, but I am just generalizing it, making things more general. So, this vector, a 2D vector, is now a linear combination of two vectors v1 and v2. Of course, this v1 and v2 has to be properly chosen and so on and so forth, but let us say we have made an intelligent choice and we have properly selected these two vectors. Now, this 2D vector could be represented as a linear combination of these two properly chosen vectors. Similarly, I can extend this concept to 3D case. In 3D case, I can have a 3D vector which I can obtain by having a linear combination of three other vectors. So, for example, I can have a vector v, I can obtain this vector v by a linear combination of v1, v2 and v3. Okay. Again, I want to generalize this idea. I am always interested in generalizing ideas to ND case. So, an n dimensional vector could be obtained by making linear combination of n vectors. Okay. So, I can have an n dimensional vector. These vectors, a set of vectors v1, v2, vn, which allows us to span a space, is known as a spanning set. Why are they allowing to span a space? Because I can change the values of these AIs, and by changing the values of AI, I can go to any point in that space. So, this is the meaning of spanning the space. Okay. So, these set of vectors which allow us to span a vector space is known as a spanning set. Okay. This is important. So, what we have learned so far in vector spaces, I can have a vector, I can obtain a vector by a linear combination of some other vectors, and normally if I want to span an n dimensional vector space, I would need n properly chosen vectors intuitively. Let us now see the idea of linearly dependent vectors. So, if this linear combination that we have just talked about, if this linear combination can be made 0 by choosing some AIs, not all of them 0. If all AIs are 0, then of course this linear combination would be 0, but what we are saying is if we can have this linear combination turning out to be 0 without having all AIs to be 0, then we say that this set of vectors is linearly dependent set. The vectors are linearly dependent on each other. Let us see why is this, and for simplicity let us just talk about the situation when we have three vectors v1, v2 and v3, and I am interested in this linear combination, and let us assume that this becomes 0 when the value of a1 is a, a2 is b and a3 is c. So, if I choose the value of a1 as a, a2 as b and a3 as c, I can make the linear combination of a1 v1 plus a2 v2 plus a3 v3 as 0, and we call this situation that these vectors v1, v2 and v3 would be linearly dependent, and let us see why is this. So, if this is 0, we can write v3 in terms of v1 and v2, and hence this means that vector v3 is dependent on vector v1 and v2. So, that is the idea behind the linear dependence of vectors. So, if the vectors are linearly dependent, you can express one vector in terms of other vectors. Okay. Let us see what it does. So, we have already said if the vectors are linearly dependent, then v3 could be expressed in terms of v1 and v2. We already know that vector v can be obtained by a linear combination of v1, v2 and v3. Now, plugging in this value v3 into this expression, what we get is v vector could be written simply like this, just plugging in the value of v3 here. Now, I can simplify this and get this. So, what does this tell me? So, if vectors are linearly dependent, I can express a vector in terms of a reduced set of vectors. So, I started by expressing a vector in terms of 3 vectors v 1, v 2 and v 3. So, I was expressing vector v in terms of 3 vectors. Now, because these vectors were linearly dependent, I can substitute one vector in terms of other vectors, and I can express this vector in terms of reduced number of vectors. Okay. So, I am killing some linear dependence. Okay. So, this is the idea of what we call as a basis set. So, you have a spanning set. So, using spanning set you were spanning the given vector space. Now, because some vectors were linearly dependent, you can start killing those linearly dependent vectors, and once you kill those linearly dependent vectors, what you end up with is a reduced set, and this reduced set is known as a basis set if there is no linear dependence between the vectors, and if this set is still able to span the complete vector space. Okay. So, we get a basis set. So, what is the idea? So, you have a vector space V, you find out the vectors v 1, v 2, v 3 and so on and so forth, let us say v n, which allows you to span this vector space. You find that some of the vectors are linearly dependent, you kill those vectors, you get a reduced set, but this reduced set is still able to span the complete space, and this reduced set where there is no linear dependence and which is still able to span the complete vector space is known as a basis set. So, let me define, because I have not defined what are linearly independent vectors. I have already defined what are linearly dependent vectors, and the definition follows straight away, there is nothing different. So, we can define linearly independent vectors as the set of vectors for which the linear combination can only be made 0 if you have all scalars being 0. So, if you made a linear combination, the linear combination only becomes 0 if you have all scalars being 0, then those set of vectors are known as linearly independent vectors. So, I can define the basis vectors again. The basis vectors is a set of vectors. If the set is linearly independent, it spans a vector space V. So, let us now see the dimension of the vector space. So, what is the dimension of the vector space? If the number of vectors in a basis set is finite, we call this as a finite dimensional space. Otherwise, it is known as infinite dimensional space. In fact, the number of vectors in the basis tells me the dimension of this space. So, if the number of vectors in a basis set is 10, then we say that the vector space is of dimension 10. If the number of vectors in the basis set is finite, of course, it is a finite dimensional vector space. If the number of vectors in the basis set is infinite, we call this as infinite dimensional vector space. Okay. So, we have come to the conclusions of today's lecture. We have seen what are waveforms. Waveforms are just continuous function of time. We have seen these waveforms are useful in digital communication codes because they are used in the transmission of signals. We have seen what are L1 and L2 signals, and these are defined based on the integration of mod of the function being finite or integration of mod square of the function being finite. We have seen that L2 space is a vector space. So, whatever we can do in a vector space can be done for the L2 space as well. We have defined what is a basis and linearly independent vectors. And in tomorrow's lecture, we will be introducing a very useful concept, and that is the concept of inner projective space, by which you would be able to find out the angle between the two signals and so on and so forth. So, thank you so much. See you next time.